Obviously these gates wouldn't necessarily be used on their own. In some cases it would be, but in many cases you would be looking at a combination of gates. And if you can see here, I've actually got an inverter connected before an OR gate. The output from the inverter here, right, is actually going to be one of the inputs, okay, to the OR gate, this one here. Right, this one's going to be one of the inputs. So if I power up the board, remember, I still have to have supply power for the inverter. You can actually see that both LEDs light, which show that both gates are operating at a high level. Remember, there's no input here to this, so this is 0, which means I get 1, which is high, and if this is 1, then my OR gate will work, because either A or B has to be on to get an output. If I supply an input to the inverter, you can actually see that the LED goes off, which means I've no longer got an input here, which means my OR gate goes off as well. If, however, I supply another input to this point here, input B, I can actually get the OR gate to work. So I'll use a red wire for that one. And you can see that the OR gate now actually works. Alright, because I now have an input to this input here. This one's high, which means the OR gate is high. This one's still off. You can see the inverter is still off, but the OR gate is now operating. So again, it would work if A or B is on. If I take this one out again, it goes off because both are actually 0. So if we look at the truth table for this combination of gates, you can see the symbol for the inverter or the NOT gate at the top here. We've also got the symbol for the OR gate here. The inputs A and B are actually at the very beginning, because whatever A is going to be, C is going to be the opposite. C is actually the output from the inverter, but then becomes one of the inputs for the OR gate. And again, we have the overall output then as being Z. So point to remember here is that whatever A is, C is the opposite, because it's an inverter. And as long as B or C is on, then I will get an output at Z. As long as B or C is 1 or high, I will get a high output at Z. So if we go down the list here, if A is 0, C is 1, as long as one of B or C is on, I will get an output. If A is 1 this time, C will be 0, it will be off. They're both off, so there is no output. As long as B or C is on, I get an output, and there is the same for the last one. So I only have one situation where I will not get an output. That is if A is on or high and B is off or low. I get an overall output of 0. So again, looking at combining gates, what we have this time is our AND gate is actually after the inverter. Again, you can see the inverter is on because the input here is low, 0, and which means I get a high output, I get 1 from the inverter. Again, this is the input to here. This is input A for the AND gate. Alright, but unlike the OR gate, it's off. Because remember, an AND gate has to have both of these inputs on or high. So to actually get the AND gate to work, again, I have to actually connect this terminal, okay, to a high voltage. And again, now you can see that the wee LED comes on, which tells me the AND gate is now acting like a closed switch completely. Right, I've got an input here which is high from the inverter. I've got an input here which is high from the positive rail at the top, which means I get an output. If I take the red wire out, the AND gate then goes off, as we would call it. Again, if I put an input to the inverter, then The output is now 0, and the input to A here is now 0, which is off. And even if I connect the top rail back in again, where this is now 1, this one is still 0, so therefore there is no output, okay, from the AND gate. So if we now look at the truth table for that combined gate circuit, again, if you look at the top here, we've got the symbol for the NOT gate or the inverter. Okay, it's the triangle with the small open circle at the point. We've got the symbol for the AND gate, which is actually a bit like a big capital D. That's how I'd always encourage you to try and remember the difference between that and the OR gate. And then we have the truth table. Now remember, whatever A is, C is going to be the complete opposite. But the AND gate is only going to work if B and C are on this time. So, if A is 0, C is 1. If A is 1, C is 0. If A is 0, C is 1. And if A is 1, C is 0. It's only going to work if B and C are on. So, we have off, on, and off. So the complete opposite to the combined gate circuit with the OR gate, where it was only off in one situation. In this case, it's only going to work in one of these situations.